Okay, in this last instructional lesson for this video series on probability, we're going to talk about transforming and combining multiple distributions. Typically this is done with normal distributions, and there are certain problems where we have to either transform one normal distribution into another normal distribution in order to calculate a probability, or we have multiple sources of variation from different distributions that have to be combined in some way. I've only seen this come up in AP statistics in high school math classes, but it's a good general thing to talk about, and really it makes all of the work we've done in normal curves that much more powerful to be able to open up a whole other range of problems. So we're going to talk about each of these topics, transforming and then separately combining multiple distributions. So some problems require that we transform one distribution into a new distribution, either by multiplying all the data values in the distribution by a fixed value, or by adding a fixed value to all the data, or both. And it'd be interesting to ask, how does multiplying or adding a constant to a data set affect the distribution? So let's explore this by performing some transformations on an example data set. So I made this data set small enough to enter by hand, but still big enough to show some results. So if you want to turn on a calculator and clear out your lists, so second mem for enter, you can go to Stat, Edit, and then you could type in L1 for list 1. You can type this data set in. So I'm going to go ahead and do this here, 20, and then so on. I'm going to put all these data in. So I would encourage you to do this on your own too. It allows you to get familiar with using the calculator as a tool to explore different ideas and concepts. So once you've got this data set in, we could figure out the center and spread, or we could plot the data. So I'll show you how I generated this for each. To plot the data, I went ahead and did a histogram. So the way we would do this is go to y equals and clear out anything there, any functions that you have for graphing, and then hit second y equal to go to statistics plot setup, go into plot 1, turn it on, and then for type you want to pick the one that looks like a bar chart, a histogram, and make sure this is set to list 1, second one for L1, and then quit out of that, zoom 9 for zoom statistics, and that will show you a histogram. Now the histogram will have something that blows it up to fill the whole screen. So because we're moving things around here, I went ahead and set the window manually, and the way you can do that is you can set the minimum to match what I did here. I set the minimum for the x's to 0, the max to 50, and then the X scale shows the bin width for each of the histogram bars, so I made that 2 and hit enter. So 0, 50, and 2. And then instead of hitting zoom 9 again, we hit graph. So that gives me a histogram of the data values in this distribution. Sort of symmetrical, a little bit of left skew, a little bit of top heavy here, but that's basically it. And there's a mean and standard deviation for this distribution. The way we would find that is by using the one variable statistics function. So if I then go to stat, and then over to calculations, and the first one variable stats, you can tell it that the data is in list 1, so we'll put second 1 if it doesn't already say that. And if there's anything in frequency list, that has to be deleted out, so that's blank. And then calculate, and that's where I'm getting that the mean of this distribution is 14.4286. The standard deviation, since this is a sample, we would use the S value, so 5.5983. If I scroll down, I can get the median, which is 15.5. That's also a measure of center. And then another measure of spread would be the interquartile range, which is abbreviated IQR. And what that is it's the difference between Q3 and Q1. Those are the quartiles. So Q1 represents the value at the 25th percentile, 1/4 of the data. And Q3 represents the value at the 75th percentile, where 3/4 of the data is below. So if you take this 19 minus this 10, that's how I got this interquartile range of 9. Okay, so the reason I did that was so we can quickly see what happens to the center, measures of spread, and what happens to the picture. So I put a blue line here approximately where the mean is, and I drew kind of a line where it shows the standard deviation on both sides here of about 5.5. Okay, so this is our original data set before we've done any transformations. So then what we're going to do is we're going to say, now let's try multiplying every value in the data set by 2. Okay, so the way we could do that is by hand. We could take the 20 and multiply by 2 and get 40, and 5 would become 10, and 15 would become 30. But what I did was I just had the calculator do that by going back into Stat, Edit, and then for List 2, I just made that. I went up and highlighted List 2 and said, let's take List 1 and multiply by 2, and then hit Enter, and that will populate this. And then we could go change the statistics plot to be looking at List 2 instead, like this, and then I'm going to hit Graph again to get the same windows. So that's how I got the picture here. And then we could also get the measures of center by rerunning one variable stats, this time on List 2. And that would give me the mean and median and standard deviation and center. Okay, so that's how I got this information. This is the original data set, and here's the transformed data set. And what I notice is that the mean appears to be about twice as far up as the original, and the standard deviation appears to be about twice as wide. So both the mean and the standard deviation were affected. And if you want to know by how much, we can compare the two. If I take either of the measures of center and divide, if I take the original measure of center mean and multiply by 2 like I did with the data, then I get the transformed mean. Same thing for median. So the measures of center are both double the measures of center for the original data. In other words, the mean of the y, if y is the transformed set, is twice the mean of the x, and the median of y is twice the median of the x. Also, the standard deviations are also doubled. So if you look at the numerical values, the standard deviation that was 5.5983 is now 11.1965, which is exactly twice the original. So the standard deviation and the IQR, the measures of the spread, are also doubled, right? So the way we could summarize that is just to say that, that the mean and the standard deviation are both multiplied by the same multiplier that we use to transform the data. Okay, so multiplication affects measures of center and it affects measures of spread. What happens if we add or subtract a constant? Okay, so we'll go back to the original data set, but this time what we're going to do is we're going to add 10 to every piece of data. So 20 becomes 30, 5 becomes 15, and so on. Right? You could do that in your calculator by going to Stat, and I'm going to go back to List 2 and clear it out, and then set it to be List 1 plus 10 this time. Reload the data, again look at the scatter plot, and again look at the standard at one variable stats to see the result. And what I see is that when we add 10 to all the pieces of data, the mean shifts, but the standard deviation is unaffected. And that makes sense because every individual piece of data is just shifting up 10 units. So it makes sense that the standard deviation and the IQR, any measure of width, of spread, would be unaffected, but measures of center would be affected by adding or also by subtracting a constant. And in fact, that's borne out in the calculated measures of center and spread. When I look at the measures of center, the new mean is 24.4, where the old mean was 14.4. The new median was 25.5, the old median was 15.5. So both of those are shifted up 10 units. But the standard deviation in the IQR for the new distribution is exactly the same as the standard deviation and IQR were the original distribution. So what we can conclude is, even though multiplication affects measures of center and spread, shifting a distribution by adding a constant or subtracting a constant affects measures of center, but it does not affect measures of spread at all. And the last thing that I decided to do was to try both at the same time. What if we doubled the data and then added 10? So if we doubled the data first and then added 10, this includes a multiplier and a shift. Okay, then you can do this for yourself if you want in the calculator. It turns out that if you look at the result, I'm just going to jump to the end here, that measures of center are affected by the multiplication of the two and their shifted 10, but the measures of spread are affected only by the multiplication of 2 and are not affected by the shift. And that means that multiplication and addition each have their own individually, independently operating features, right? The multiplication affects measures of center and spread, and the addition affects only the multiplications of centers. And those two effects operate independently of each other. Okay, so the way I would summarize this is this way. When we transform a distribution by multiplying or dividing, dividing is just multiplying by a fraction, or by adding or subtracting a constant to every element, then the multiplying and dividing affects both center and spread because the low numbers are brought up and the high numbers are brought up even more. But adding and subtracting just shifts, so only measures of center are affected. So you could summarize it this way. If you have a distribution y, which is formed by taking an initial distribution and multiplying by a and adding or subtracting b, then the mean will be the multiplication of a plus or minus the shift, but the standard deviation will only include the multiplication effect and not the shift. Okay, so that's an important idea. Let's see an example that puts this to use. Let's say that in your area, monthly residential electricity costs 12 cents per kilowatt hour, in addition to a 25% fixed fee for your bill. So if your monthly power usage varies from month to month, and it varies in according to a normal distribution with a mean of, say, 900 kilowatt hours and a standard deviation of 200 kilowatt hours, then what would the probability be that an individual monthly power bill will be less than $100? Okay, so for us to compute that, we're going to need normal CDF, and we're going to have a normal curve. But the normal curve is going to have to be the normal curve representing the total monthly bill cost. The normal curve we have right now is about the power usage. So we're going to have to take a power usage normal curve and transform it into a cost normal curve. Okay, there is a single distribution, power usage, but we can transform it. And the formula for transforming that is we take the kilowatt hours, we multiply by the rate of 12 cents per kilowatt hour, and then we add on the fixed $25 cost. So this includes both a multiplier and also an addition. So the curve that we have right now, we know the mean of the power usage is 900 and the standard deviation is 200. What we need to figure out is what is the mean and standard deviation of the corresponding transformed cost. Okay, so the multiplier, the 12 cents, that part will affect both mean and standard deviation because multipliers affect measures of center and spread, right? But the addition, the $25 fixed fee, will only affect the measure of center, the mean. So that means that the mean of the cost will be the multiplier times the mean of the power curve plus the constant addition. So it's going to be 0.12, the multiplier, times the mean of this distribution, which is 900, plus the shift of 25, which means that the mean cost will be $133. So both the multiplier and the addition affect the mean. But the standard deviation of the cost will only be affected by the multiplier. It will not be affected by the $25 shift. So that means that the mean of the cost will be the standard deviation of the cost will be the standard deviation of the power usage times the multiplier. So 200 times 12, or $24. That's the standard deviation of the cost curve. And now that we have a mean and standard deviation for cost, we can use this normal distribution along with normal CDF to find the probability that an individual monthly power bill will be less than $100, because $100 is about here, and that means that the probability of being lower than that would be normal CDF from negative infinity to 100 as the upper boundary, with a mean of $133, standard deviation 24, and that will occur about 8.5% of the time. Okay, so that illustrates where sometimes we need to transform. In this case, we had to transform power usage to cost, and we use those rules. A good indication that you need to do that is if you see units changing. You have a distribution, you're being asked to find a probability of something else, and the units are not the same. If that's true, some kind of transformation is going on. Okay, the second thing that we sometimes have to do is we have multiple normal distributions that represent different variables that are being combined in some way. Okay, so let's say we have two random variables, x and y, and each of them vary randomly around their own mean with their own standard deviation. I could define a new random variable, z, that represents, say, x minus y. Okay, and that would be the mean and standard deviation. We would need to figure out what the mean and standard deviation of this new variable z would be. Okay, so let's say x and y have the following means and standard deviations. Let's say x has has a mean value of 100 with a standard deviation of 10. And let's say that the distribution for y has centered at 30 with a standard deviation of 6. So our new our value z, it also has a mean, right? And mean values are known. There's no variation in the means. There's no uncertainty in the means. And so therefore, I can just use the mean of the z will just exactly follow whatever the algebraic expression is for determining that variable. So if z is x minus y, then the mean of z will just be the mean of x minus the mean of y. And there's no uncertainty there. So it's just going to be 100 minus 30, and that means that the z, this new distribution, will definitely be centered at 70. Okay? It's trickier to find the spread, the standard deviation, and that's because there's actually two sources of variability. We have variation in x that's unknown, and we have variation in y that's unknown. Okay, so let's take a look at some kind of values and see what that means for the z corresponding z value. Most of the values will be near the means. So that means if I have a value near the mean of x and I have a value near the mean of y, then the value of z will be near the mean of z, right? Because the mean x is 100, the mean y is 30. So 100 minus 30 will be around 70, right? So most of the values will tend to be near the mean of z. Okay, but what if I had a really high value of x and I happen to have a really high value of y? Since they're both shifted up, right, the shiftedness, if you want to think of it that way, kind of cancel out, right? Since I'm talking about x minus y, if I have something that's 100 plus a certain amount and I have 30 plus a certain amount, that value minus this value is also going to be fairly close to the mean of 70. Okay. I could also have, say, an unusually low value for x and an unusually low value for y, and this x minus this y would still be 70 apart. So that would also produce a value fairly near the mean of the z distribution. Okay, but what if I had this situation? What if I had an unusually high value of x paired with an unusually low value of y? So that means that I would have an extra high x value, right? And then I would be subtracting a little tiny y value, which means I would have an unusually large difference. And that means that this value here in the z distribution would be really high, much higher than the individual x and y were. In other words, the distance here would be larger than the individual distances in the x and y direction. Similarly, if I had an unusually low x value paired with an unusually high y value, the difference would be abnormally low. A lower starting value taking away a much larger value produces an unusually low value for z that's even larger than the individual values themselves, right? So all of this is just to show that whenever you have situations where you're subtracting, even if you're subtracting, since there are two sources of variability, the new distribution will always have an increased, wider amount of variability than the individual distributions that were the source values. The question is, how do we calculate this increased variability, the new distribution standard deviation? Okay, so I'm going to try to provide an intuitive explanation for the combined standard deviation calculation. If we can assume that the two sources of variability for x and y are varying independently, and this is a really critical point, we can really only analyze this in this way if we know that the variation in x and the variation in y are completely disconnected from each other, they're independent. So if that's true, then the variation of one of the variables can't affect the variation of the other variable. We could picture this by imagining that each variation takes place along two orthogonal axes that are at right angles to each other like this. So x in one direction, y in the other. Okay. If we had a data value that's one standard deviation away from the mean of each distribution, then they're going to appear at a particular x and y value. So if we have this point here, which is a certain distance, say above the mean in the x direction, then that would be one standard deviation in this direction, and also one standard deviation for the y that's also away from its mean, and that would be at an orthogonal direction like this. Then you could kind of picture that as a point in this two-dimensional space. Okay, then the two independently varying values, they would form the legs of a right triangle, and the hypotenuse could be thought of as a measure of the overall variation from the origin, right? But the origin would be where the means are, including the mean of the z distribution. So that could be thought of as a representation. That hypotenuse length is the representation of the amount of variation of the combined z distribution. Right, and therefore the mean of that, right? So we could find this this hypotenuse just with the Pythagorean theorem, right? The standard deviation squared for z would just be equal to the standard deviation squared for x plus the standard deviation squared for y. Okay, so this idea is sometimes referred to as the Pythagorean theorem of statistics, right? It only works when we have a right triangle, and therefore we have to have that x and y are varying independently. Okay. Another way to think of it, and the way I think of it, is the standard deviation squared has a name. That particular quantity, a standard deviation squared, is referred to as the variance. Okay, so the way I think of it is that the combined variance is equal to the sum of the individual variances. So if x is providing random variation and y is providing random variation, then regardless of whether I'm adding or subtracting x and y to make the z, the combined variation is always the sum of the individual variance of the sources. Okay? So for our example, that means that the standard deviation for z squared would be the standard deviation for x squared plus the standard deviation for y squared. And since the standard deviation for x is 10 and the standard deviation for y is 6, we can plug those numbers in here, and then just compute that by taking the square root to find the standard deviation for z and find out that it's 11.6. And remember we said it would be higher than the individual source variabilities. Y only varied with a standard deviation of 6, x varied with a standard deviation of 10, but that means z varies with a standard deviation of 11.66. Okay, all of these ideas, by the way, work similarly if you're combining more than two distributions. Let's say that we had 4 independently random variables, a, b, c, and d. They all varied, they all had means, they all had standard deviations, but they were all varying independently from each other. We define a new variable e, that's the a variable plus the b variable minus c minus d. So the means are always determined by the defining algebraic expression. So that means the mean of E would be the mean of A plus the mean of B minus the mean of C minus the mean of D. But because each source of variability will increase the overall variation, the variances always add. So that means that the standard deviation of E squared equals the standard deviation of A squared plus the standard deviation of B squared plus the standard deviation of C squared plus the standard deviation of D squared. These are all pluses, even where we had minuses in the original distribution, because variances always add, right? Whenever you add another source of variability, the overall variability always increases. Okay, so let's take an example to see how this would work. Let's say that at your house in Hawaii, which has very little variation in outside temperatures throughout the year, you pay an electric bill and you pay a natural gas bill at your home. So random variations do occur month by month that cause both of these bills to go up or down, and the costs of the bills turn out to be independent of each other. So the electric bill variation completely disconnected from the gas bill. Okay, if the electric bill cost is a normal distribution with a mean of $40 and a standard deviation of $12, and the gas bill cost is $25 mean with a standard deviation of 8, what is the mean and standard deviation of the total cost of these two bills? Okay, so you could start by writing an algebraic expression that represents the situation. The total cost is the electric cost plus the gas, T equals E plus G. Okay, so what I think in my mind is each of these is a source of variation. So I picture a distribution for each. And sometimes you even write this just to kind of get my thinking straight. There's a distribution for the total cost, and that's equal to the distribution plus of the electric plus the distribution of the gas. Okay, so in this case, we're going to know some of the means and standard deviations, and we're going to need to find others. So here, we know that the mean of the electric bill is 50 with a standard deviation of 40 with a standard deviation of 12, and for the gas bill, the mean is 25 with a standard deviation of 8. And we're trying to find the mean and the standard deviation of the total cost so that maybe later I can turn this into a probability problem. And we'll do that actually. So the means are always computed just by replicating the algebraic expression. So the mean of the total will be the mean of the electric plus the mean of the gas. Because there's no variability, it's just 40 plus 25 or 65. So the average bill total between gas and electric will be $65. Okay. For the standard deviations, we compute that using the ideas that variances always add. So the standard deviation squared for total is the standard deviation for electric squared plus the standard deviation for gas squared. We can just plug in the values for the standard deviations and then take the square root to convert the variance back to standard deviation. That's $14.41. So that means that I now have the distribution for the total bill. Okay, so we could now, for example, turn this into a probability problem. We might ask, what's the probability that a selected month's combined utility bill will be more than $70? So we could go ahead and put a boundary at $70, shade the area that's more than that, and then use a normal CDF function to compute the probability. It would be the normal CDF from 70 to positive infinity with a mean of 65 and a standard deviation of 14.42. That turns out to be 36.44%. Okay, so just to summarize what we talked about, there are two kind of related but separate ideas. When we transform a single distribution by multiplying or dividing or adding or subtracting a constant to every element, the multiplying and dividing part affects both center and spread, but the adding and subtracting part affects only the center. Okay? If we are combining multiple distributions with their own independent sources of variation, then you could define an algebraic expression for how they should be combined with addition and subtraction. The means are always determined by the algebraic expression, but because each source of variable increases overall variation, the variances add. And that means we always have adding, even when we have subtracting in the defining expression. However, we must know for certain that the variables are all varying independently of one another. If that's not true, we can still compute the combined mean, but we can't say anything about the standard deviation without getting into advanced linear algebra ideas. Okay, so that's it for the last topic.